Hello, continuing our discussion of implementing database systems, moving into chapter 2, which deals with database system concepts and architecture. The things that we'll be talking about today include data models and their categories, the history of data models, schemas, instances, and states, three schema architecture, uh, data independence, DBMS languages and interfaces, database system utilities and tools, centralized and client-server architectures, and then classification of DBMSs. Starting off with database models or data models. A data model is a set of concepts to describe the structure of a database, the operations, the manipulation of these structures, and certain constraints that the database should obey. So basically, it describes what could and should be done and what cannot. Data model structures and constraints. Constructs are used to define the data structure or the database structure. Constructs typically include elements and their data type, as well as groups of elements such as entities, records, and tables, and relationships among these items. And those relationships are ways that they have interaction with each other. Constraints specify some restriction on valid data, so it's essentially what is allowed or not allowed. These constraints must be enforced at all times. Data model operations. These operations are used to specify database retrievals and updates by referring to the constructs of the data model. Operations on the data model may include basic model operations such as inserts, deletes, updates, and user-defined operations such as compute student GPA, update inventory, so more complex aggregate sort of operations. Conceptual, high-level, and semantic data models provide concepts that are close to the way many users perceive data, also called entity-based or object-based data models. Physical, low-level internal data models provide concepts that describe details of how data is stored in the computer. These are usually specified in an ad hoc manner through database management system design and administration user manuals or manuals. Implementation or representation of these data models provide concepts that fall between the above two, used by many commercial database management implementations, such as relational data models used in many commercial systems. Self-describing data models combine the description of data with the data values, and examples of this include things like XML key value stores and some NoSQL systems, which is also a key value store. Database schemas. This is a description of a database. This includes a description of the database structure, data types, and constraints of or on the data within the database. Schema design is an illustrative display of many, if not most, of a database's schema. Schema construct is a component of the schema or an object within the schema, for example, a student or a course. A database state is the actual data stored in the database at a particular moment in time. This includes the collection of all data in the database, also called database instance or occurrence of or snapshot. The term instance is also applied to an individual database component, for example, a record instance, a table instance, or an entity instance. Database state refers to the content of the database at a moment in time, where the initial data state refers to the database state when it's initially loaded into the system. Valid state is a state that satisfies the structure and constraints of the database. Distinction, the database schema changes very infrequently. The database state changes pretty much every time the database is updated, so anytime a transaction occurs. Schema is also called the intention, and state is also called the extension. Here is an example of a database schema. This is revisiting what we discussed in the first chapter, which is a schema diagram for a set of university-related students and courses. This is a particular example of the state of that schema at a given point in time for one of the tables, in this case, course. A similar sort of state of a different table, this time section of a moment in time, and grade report as well. And then lastly, prerequisite. The three schema architecture was proposed to support database management characteristics of program-data independence. It supports multiple views of the data, not explicitly used in commercial database management systems, programs, or products, but it has been useful in explaining database system organization. Whenever we talk about the three schema architecture, it defines the DBMS schema at three levels. Internal schema, that is at this internal level to describe the physical storage structures and access paths, for example, indexes. Typically uses a physical data model. Conceptual schema at the concept level to describe the structure and constraints of the whole database for a community of users, uses a conceptual or an implementation data model. An external schema at the external level to describe the various user views, usually uses the same data model as the conceptual schema. Figure 2.2 is the three schema architecture for a particular scenario. The internal level is talking about how things are actually being stored. The conceptual level is kind of the conceptual internal mapping, and then the external is how the world views it. The three schema architecture on the third slide. Mapping among schema levels are needed to transform request and data. Programs refer to the external schema and are mapped by the DBMS to the internal schema for execution. Data extracted from the internal DBMS level is reformatted to match the user's external view, formatting the results of an SQL query for display on a web page is a good example. Data independence, we talked about this a little bit in the first chapter. Logical data independence, the capacity to change the conceptual schema without having to change the external schema and their associated application programs. Physical data independence, the capacity to change the internal schema without having to change the conceptual schema. For example, the internal schema may be changed when a certain file structure is recognized or new indexes are created to improve database performance. When a schema at a lower level is changed, only the mappings between the schema and the higher level schema need to be changed in a DBMS that fully supports data independence. The higher level schemas themselves are unchanged. Hence, the application program need not be changed since they refer to the external schema. DDL, data definition language, DML, data manipulation language, high-level and non-procedural languages. These include things like relational SQL language, SQL, may be used in a standalone way or may be embedded in a programming language. Low-level or procedural language, these must be embedded in a programming language. So these are basically languages that are associated with database systems. Data definition language used by DBAs and database designers to specify the conceptual schema of a database. In many DBMSs, the DDL is also used to define internal and external views. In some DBMSs, separate storage definition language, SDL, and view definition language, VDL, are used to define internal and external schemas. SDL is typically realized via DBMS commands provided to a DBA and database designer. DML, data manipulation languages, is used to specify retrieval and updates. DML commands, data sublanguage, can be embedded in a general purpose programming language, host language, such as COBOL, C, C#, .NET, Java, pretty much any language that uses some form of a driver to talk to the database. A library function can be also provided to access DBMSs from a programming language. That's typically a driver like ODBC, JDBC, and so on, ADO. Alternatively, standalone DML commands can be applied directly, called a query language, usually through some sort of a query interface. There are types of data manipulation languages. High-level or non-procedural language, a good example of that is SQL relational language. It's set-oriented and specify what data to retrieve rather than how to retrieve it. Declarative is the term for this. It is a declarative language, so you just say what should happen, not how. Low-level or procedural languages retrieve data one record at a time, construct such a looping as needed to retrieve multiple records, and along with positional pointers, very much specifying how it is being done. DBMS interfaces, standalone query language interface, for example, entering SQL queries at the DBMS interactive SQL interface, so typing something inside of a query window. Programmer interfaces for embedding a DML in programming languages. User-friendly interfaces, these are menu-driven, form-based, graphic-based sort of interfaces, typically things like a dashboard or some sort of query by example environment. Mobile interfaces, these are interfaces allowing users to perform transactions using mobile applications. Programmer interfaces for embedding DML in programming languages. Embedded approaches, for example, embedding SQL for C or C++, SQL for Java. Procedural call approaches using something like JDBC for Java, ODBC for other programming languages such as APIs. Database programming language approach is using something like Oracle, PLS, QL, and it's essentially a programming language. It's a variant of SQL. Language incorporates SQL and many of the data types, as well as some integral components. Script languages such as PHP, Python, Java, or JavaScript, and so on are used to write database programs. User-friendly database management system interfaces. These are typically menu-based, often through the web browser, popular for browsing on the web, form-based, designed for naive users, used for filling in forms or filling in entries via forms. Graphic-based, potentially have point and click, drag and drop, specify a query or a schema diagram. Natural language potentially includes things that are written in an English-like form, and there's oftentimes a combination of the above, so they take pieces from each and combine them together. There are other types of database management system interfaces. For example, natural language, where you essentially do free text as a query, speech, where you say what you want, web browsers with keyword searches, parametric searches, such as bank tellers using certain function keys, interfaces for the DBA, creating user accounts, granting authorizations, setting system parameters, and so on. Some of the utilities are associated with database systems. They're used to perform things such as loading data stored into files into a database, essentially a bulk import. Includes data conversion tools, back up the database periodically on tape or disk. Nobody uses tape anymore. Reorganizing database file structures, performing monitoring utilities, report generation utilities, some other functions such as sorting, monitoring, and potentially data compression. The other tools include things like data dictionaries, repositories. These are used to store schema descriptions and other information such as design decisions, application program descriptions, user interfaces, standards, and so on. Active Data Dictionary is accessed by DBMS systems and users and database administrators. Passive Data Dictionary is accessed by users and DBAs only. Application development environments and case tools, computer-aided software engineering tools. These include things such as Power Builder by Sybase, JBuilder by Borland, or JDeveloper 10G by Oracle. Typical DBMS components module. This diagram shows how various components are talking together. Notice that we've extended what we saw previously before and went into greater detail. We now know a lot more about how a user's query comes in, goes through a query compiler. There's a query optimizer in the mix, and then at some point goes down to the database processor. So this gives you a hint as to some of the complexity that goes into various database systems. So when we talk about centralized and client-server architectures, centralized database management systems combine everything into a single system, including the DBMS software, hardware, application programs, user interfaces that are accessing the program, and so on. Users can still connect through some sort of a remote terminal, maybe even a web browser, but all the processing is done in a centralized location. Here's an example of a centralized architecture, and all of this is in one location. A basic two-tier client-server architecture, specialized servers with specialized functions. You typically separate things across multiple computers, and not everything is done on a single box. So you have a print server, file server, database management server, web server, email server, and so on. This is called separation of concerns, generally a very good idea. Clients can actualize the specialized servers as needed, and a server does a particular set of things. Here's an example of what that looks like visually, where you have multiple clients that are talking to the various types of servers, typically over a network. Clients provide appropriate interfaces through client software modules to access and utilize the various server resources. Clients may be diskless machines or PCs or workstations with disks and with only client software installed. You typically connect to the servers via some sort of a network, be it a LAN, wireless, whatever it might be. DBMS Server provides database query and transactional services to the clients. Relational database management systems servers are often called SQL servers, query servers, or transaction servers. Applications running on clients utilize an API to access server databases via standard interfaces such as ODBC or JDBC. Continuing the discussion on two-tier client-server architectures, clients and servers must install appropriate client modules and clients module software for ODBC and JDBC to work. You essentially have to install the driver. A client program may connect to multiple DBMSs, sometimes called data sources. In general, data sources can be files or other DBMS, non-DBMS software that manages data. We'll talk about Chapter 10 for database programming. The three-tier client-server architecture, this is typically done in a lot of web applications. There's an intermediate layer called an application server or web server. It stores the data, stores the web connectivity software and the business logic for the application used to access the corresponding data from the database server. Acts like a conduit for sending partially processed data between the database server and the clients. Three-tier architectures can enhance security. Database server only is accessible from the middle tier. Clients cannot directly access the database server. Clients contains user interfaces and browsers. The client is typically a PC or a mobile device of some sort. This is the architecture of a typical three-tier client-server architecture. This has changed somewhat, but not a whole lot. Some of the application program is actually shifted down onto the client with the advent of server-side code, such as JavaScript and so on, but it's the same basic kind of concept. Classification of database management systems. Based on the data model used. For example, the legacy ones are things like network and hierarchical. Currently used are things like relational, object-oriented, or object relational. Recent technologies include things like key value, storage systems, NoSQL system, document-based, column-based, graph-based, key value-based, and native XML or JSON data stores. Other classifications include things like single user, typically on a single computer, versus multiple user, centralized, where everything happens on essentially one computer, versus distributed, which involves multiple computers. There are variations on DBMS systems where there is homogeneous, where everything is essentially the same, heterogeneous, where everything is potentially quite different. Federated or multi-database systems. Participating databases are loosely coupled with a high degree of autonomy, and distributed database systems now comes to be known as client-server-based database systems because they do not totally, they do not support a totally distributed environment, but rather a set of database servers supporting a set of clients. There's been a certain change in this with the advent of some of the cloud technologies and so on, to where you actually do have distributed database systems that are supporting distributed in a true distributed way that look kind of like a single server. It's something in the category of new SQL versus NoSQL, so a slight variation. When we talk about database management systems, we have to consider cost. The cost range goes from free open source systems to commercial off the shelf that cost considerably more. Example of free relational DBMSs is things like Postgres or MySQL. Commercial DBMSs offer additional specialized modules, time series analysis, spatial modules, document models, XML modules, additional functionality when purchased separately, sometimes called cartridges in the case of Oracle, or blades. Different licensing options exist, such as site license, maximum number of concurrent users, seat licenses, and so on. A key thing to consider whenever you're talking about cost of open source systems, they may not be free in the total sense. You may not have to pay for the software, but that's not to say it's free, because you have to have somebody learning how to use it, knowing how to use it, staying up to date as it evolves, dealing with issues that may not be supported by some vendor, and that's where the premium or the freemium sort of approach of a lot of what are like MySQL does offer a free version, but not necessarily for commercial use. Other considerations, the type of access paths within the database. So you might potentially be using something like an inverted database, or sorry, inverted index-based approach, such as database. Or fully indexed using keywords, something used in search engines. General purpose versus special purpose. Airline reservations are going to be quite different than a traditional OLAP or OLTP system. So some additional information here. When you talk about the history, things started off kind of with network, hierarchical, relational, object-oriented data models and object relational models. The history of data models. The network model was first introduced back at Honeywell in 1964 or so. It was adopted heavily due to its support by Codicil. It's a conference of data system languages. Reported it in 1971. It was later implemented in a large variety of systems. The biggest advantage you had with that was the network model was able to model complex relationships and represent schematics of add, delete on the relationships, can handle most situations for modeling using record types and relation types. Language is navigational, uses constructs like find member, find owner, find next within a set, and get. Programmers can do optimal navigation through the database. Disadvantages is navigational procedural nature of the language. The database contains a complex array of pointers that threads through a set of records, little scope for automated query optimization. The hierarchical data model, initially implemented as a joint effort between IBM and North American Rockwell in 1965, resulted in an IMS family of systems. IBM's IMS product had and still has a large number of customers. It's a hierarchical model, was formed based upon IMS systems. Other systems are based on this model, such as System 2K, SAS Inc. Advantages: it's simple to construct and operate, corresponds to a number of natural hierarchical organizational domains. Language is simple, uses constructs like get unique, get next within, parent. Disadvantage: navigation and procedural nature of the language. Database is visualized as linear arrangement of records, and there's little scope for query optimization. Moving on to the relational model proposed by Codd in 70 from IBM. It was the first commercial system, and its first commercial implementation was in 1981 to 1982. It's now used in several commercial products. Probably most of them implement some variation of it. There's several open source implementations of it as well. It's most dominant in a lot of ways, when you think relational database systems, it's definitely what you're going to see. The SQL, there's lots of different standards, but very few programming languages actually implement the standards explicitly. We'll talk about chapters 5 through 11 because it is such a big part of the database world. Object-oriented data models, there's several models that have been proposed. One set of compromising models is around object-oriented programming languages such as C++ or Smalltalk, which is Gemstone. Additionally, systems like O2, Orion, and so on have been implemented. Object-oriented database standards have been proposed. Chapter 12 talks about this briefly. Object relational models, this is a tend to mix object models with relational. It started with Informix, Universal Server. Relational systems incorporate concepts from object databases leading to object relational models, exemplified in the versions of Oracle DB2, SQL Server, and other database management systems. Current trend by relational DBMS vendors is to extend relational database management systems with capabilities to process XML text and other data types. Object relational is receding in the marketplace. We don't necessarily hear it near as much. And so in summary, we talked a bit about database or data modeling systems and their categories, schemas, instances and states, three schema architecture, data independence, DBMS language and interfaces, database system utilities and tools, database system environments, centralized and client server architectures, and classifications of DBMS systems. And then we closed out with the history of data models. And with that, we've reached the end of chapter 2. Stay safe, and I will speak with you next week.